This is the graph domain and range of a logarithmic function. So we've got g of x equals negative log base 2 of x minus 3. So the way I approach these is I think about what would be the parent function, and I think about, or I figure out what that graph would look like, and then I apply the transformations. So this particular function, our parent would be y equals log base 2 of x. And then the transformations for our g of x, the final answer kind of graph that we're going to want. So we have, remember, any sort of shifting up or down has to happen last. So we need to reflect first, reflect about. So it would be, since this minus sign is outside the log, it's not on the x, we're going to reflect about the x-axis so that it reflects it kind of vertically. So reflect about the x-axis. And then shift down 3. Okay, but before we can do that, we have to know what the heck this thing looks like, and this is kind of new for us. So I'm going to rearrange this log equation and write it in exponential form. So the base 2 is raised to the exponent y, so the log is an exponent, and that should be equal to x. So I'm going to pick values for y and then figure out the x to fill in this table sort of backwards. So I'll do, I don't know, how about negative 2, negative 1, 0, 1, 2. But you might notice in the directions it says we only need to plot 2 points, but I just want to have a better understanding of what this graph looks like. So I'm doing more than 2, obviously. Okay, 2 to the negative 2 is going to be 1 over 2 squared, or 1/4. And then 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. So just by the way, with a basic log graph, the parent function, you always are going to have this x-intercept at 1, 0. And then the base of your log, you're always going to have that base comma 1. And then reciprocal of the base at negative 1. So you're always going to get those like kind of 3 key points. Okay, so you also might notice, why can I not get this to, okay, let me get rid of that. I'm trying to draw this so it's like right on a grid line. Oh dear. Okay, so you might notice that the x's are all positive, and that's because a logarithm has a domain of only positive values. I don't know why I'm having so much trouble drawing this stuff. Okay, so let's see. I'm going to scale this though kind of large. So this, let's make that x equals 1, 2, 3, 4. That's what we need. Okay, and then 1, 2, 1, 2, kind of. Okay, so 1/4 negative 2. So as kind of close as I can get, almost down at negative 2. And then 1/2 is at negative 1, so about there. And then 1, 0. And then 2, 1. And 4, 2. And so we have this guy. Almost kind of looks like it might look like a like square root of x, but not quite. It doesn't actually increase as quickly, I guess, once it gets kind of out here. Anyway, okay, so this is our parent function. So now we're going to have to flip this thing around and subtract 3. And you can actually do that in the table of values. So if I maybe just take these 3 key points, since we're only need to actually plot 2 points for our final answer graph, maybe I'll change colors. So we'll do this g of x stuff in red. So if I take my table of values, and I'll just take the 1/2, 1, and 2 for my x's. And then my y for my parent function was negative 1, 0, 1. And so if I then have a new column, where I make that negative and then subtract 3. Let's see what happens. So I take the negative is positive 1, and then subtract 3, I get negative 2. Now, of course, you could do this here on this graph, right? So it's this point. I flip it up and then subtract, subtract 3, and it's going to go kind of down there. So then if I take the 0 and make it negative, that's still 0. Subtracting 3, I get negative 3. And then if I take this 1, make it negative, subtract 3, I get negative 4. So let's just see what this looks like. So 1/2 is now at negative 2. So here. 1 is at negative 3 here. And I should have extended this guy a little bit more. 2 is at negative 4. So to me, that makes sense that it's upside down because we reflected it. And it got shifted down 3. And so also, the vertical asymptote didn't change, right? If you flip a vertical line and shift it down, it's still the same vertical line. And so you just take whatever's inside your logarithm, you set that equal to 0, that's your vertical asymptote. So it's the same x equals 0 or y-axis vertical asymptote. Okay. So finally, let's plot this stuff. So we're plotting the red graph. So I'll do the whole number one. So 1, negative 3, right here, and then 2, negative 4, right there. And if you want, you can still plot ones with fractions, even if it doesn't let you like click it on the graph. You just type it in with this plot a point thing. So 1/2 negative 2. Oh, I thought it would stay there. Okay, I have to like click plot point, I guess. I suppose that makes sense. Negative 2. There. Okay, and then vertical asymptote and graph a function. And that looks like this red one, right? So that looks good. And so you can check it with a graphing calculator, even if you're not sure how to put in log base 2, just use natural log, and it should be pretty similar to that. And so the domain and range are going to be the same as for any basic log function, because we didn't shift left or right, so the domain is still going to be 0 to infinity with parentheses. And the range is always going to be negative infinity to infinity for a log, or at least the ones that we're going to be dealing with. Okay, so there we go. Yep, correct. So let me see if I can find maybe one that's... Oh, okay, this will be a good one. So this one's a little different because the shift is inside the parentheses. So this is going to change our domain and our vertical asymptote. So that's a good one to look at. So, okay. So looking at this g of x, log base 3 of x plus 2, and then minus 1. The parent function would be y equals log base 3 of x. So I'm going to figure out what that graph looks like and get at least 3 points on that graph. And then apply my transformations. And both of these transformations are going to be shifting, right? So the g of x is log base 3 of x plus 2, and then minus 1. And so we're going to shift left 2, and then we'll shift down 1. And if all you have is shifting, it actually doesn't make a difference what order you go in, but I think it's good to stay consistent. Okay, so if we rearrange this guy, 3 to the y equals x, and so we can pick our values for y. And I'm just going to do negative 1, 0, 1. And so then if I do 3 to the negative 1, I get 1/3. 3 to the 0 is 1, and 3 to the 1 is 3. And so these are those 3 key points that we're always going to have, right? Reciprocal of the base, negative 1, 1, 0, and then base 1. But of course you could do more if you wanted to. Oh, actually, you know what? Let me move this over, because we're going to shift this thing left too. Ugh, gosh, I don't know why I can't draw a straight line on this thing. Okay, something like that. Sort of. Okay, so I'm going to scale this a little bigger again, just to make it easier to see for these sort of fraction ones. Okay, 1/3 -1, so like here, maybe. And then 1, 0, and then 3, 1. All right, so I'll switch to blue for our g of x. So when we shift this thing left 2, and so you can, maybe I should make this bigger. You can just go ahead and like do this on your paper with the shifting and the whatever. But if we shift left 2, that looks so bad. And then down 1, we're going to get here. And you can kind of, you know, if you're doing this carefully, you can tell this point is at -1, 1, and you could go ahead and even plot it over there. And then shift this guy left to down 1. It's actually going to end up as an x-intercept. And then we had this point that was at 1/3 -1, and we're just going to do the best we can, knowing that we only really need to plot 2 points on Alex. But if I shift it left 2, it's going to be about there, and then down 1, so about there. But really, this point is going to help us understand what's going on with the vertical asymptote. So the vertical asymptote is also going to shift left 2. So if I take my x plus 2 and set it equal to 0, I get x equals -2, right? So I'm taking what's inside the log. And so I am going to have this vertical asymptote here at x equals -2. And so the graph is going to look kind of like this for the final answer. So just to see how it works, the trick that we did with the last one, where we actually just kind of applied the transformations to our points. So it's going to be a little bit trickier for this one. So if we do our 1/3 -1, 1, 0, 3, 1. So, because we're going to have to change the x and the y. So for the x, when we shift left 2, we're going to actually have to subtract 2, right? We always have to do the opposite. So this goes to being whatever 1/3 minus 2 is for our new x and g of x. And then -1, we shift down 1, so subtract 1 for -1, we get to -2. So what the heck is 1/3 minus 2? I should be able to tell you guys that. So that would be 6/3, -5/3. Okay, and then so if I take this 1 and subtract 2, I'm going to get -1. 0 minus 1 is -1. 3 minus 2 is 1. 1 minus 1 is 0. And so we got those 2 points right here. So whichever method you think is going to be easier for you to do is what you should do. You don't have to do all of this. Okay, so I need to plot some points. So -1, 1, right there. And then 1, 0. We got, again, kind of by coincidence. And the vertical asymptote is now at x equals -2. And so there we are. And so our domain, instead of being from 0 to infinity, is going to be from -2 to infinity. But the range is still -infinity to infinity. Okay, check. Yay.